Hello everyone, my name is Ali Hen and my student ID is MAT2409001. Today I'm going to present a topic from my mathematical analysis course, Lipchitz continuous function. This concept is a very powerful tool that helps us understand the stability of function in a deeper way. Okay, in this presentation, I will start with the motivation. Why do we need this concept? Then I will provide the formal definition and prove a key property that connects it to uniform continuity. Then we'll look at two examples to see when it works and when it fails. Finally, there will be a summary. Why do we Lipchitz continuity? Well, as we have learned, standard continuity just tells us that a function doesn't have jumps. But sometimes that's not enough. Even if a function is continuous, it might change its value extremely fast. Uniform continuity is better, but it can be hard to check using the epsilon delta definition. This is where Lipchitz continuity comes in. Think of it as a speed limit of functions. It tells us that the function cannot grow faster than center rate. This makes the function much more predictable and stable, which is crucial in solving differential equations. Let's see the formal definition. A function f d2r is called Lipchitz continuous function if there is a constant c larger than 0, such that for all x, y in D, there exists the absolute value of fx minus fy is less than or equal to c times the absolute value x minus y. Then the constant c is the Lipchitz constant. Geometrically, this means the slope of the second line is always bounded. It prevents the function from having an infinite steepness at any point. Okay, then let's see a key property. One of the most important theorems is that Lipchitz continuity implies uniform continuity. Let's walk through the proof. If f is Lipchitz on D, then f is also uniformly continuous on D. This is a theorem. Let's prove it. We start with the inequality. The absolute value of fx minus fy is less than or equal to c times the absolute value x minus y. For any epsilon, we can choose the delta equal to epsilon over c. If the absolute value of x minus y is less than delta, then the absolute value of fx minus fy is less than or equal to c times the absolute value c minus y less than c times the epsilon over c equal to epsilon. Since delta only depends on epsilon, this proves the uniform continuity. Okay, know the property. We can see some example. The one is a linear case. Let's see the concrete example. Consider the linear function fx equal to 3x plus 1 on R. And this is the image of the function. We have the result. This function is Lipchitz continuous. Let's see how to prove it. We know the definition, the absolute value fx minus fy. In this case, it equals to 3 times the absolute value x minus y. Oh, jump the step. 3x plus 1 minus 3y plus 1. This form, we can know the constant, Lipchitz constant is 3. So fx is Lipchitz continuous. This makes perfect sense because the slope of lines is constant, since the slope is always 3. It is obvious bounded, so every linear function is Lipchitz continuous. This is works. Let's see when does it fail. The function is gx equals to the square root of x on the interval 0 from 0 to 1. This is the image of the function. Let's see why it doesn't work. We write it down. Let's y equal to 0, then gx minus g0 equals to square root of x minus 0. We want it less than or equal to a constant c times the absolute value of x minus 0. Then we can get the square root of x less than or equals to c times the x. We can get 3c needs to larger than or equal to 1 over square root of x. But from image we can say when x close to 0, then the 1 over square root of x is approaching to infinity. So there is no constant can satisfy the c. So the function is not Lipchitz continuous. Okay, let's see. That's all for today's share. Why is this important? To summarize, Lipchitz continuity is a strong form of continuity. It acts as a bridge between simple continuity and differentiability. By bounding the stretch or speed of a function, it ensures that the solution to problems, especially in differential equations, x and are unique. It's a fundamental concept that gives us a clear geometric and analytic picture of well-behaved functions. This is a reference of today's presentation. Okay, that's all for my presentation. Thank you for your listening.